All right. Okay. Well, happy Friday, and thanks for being here. Um, I guess we'll take a look. I've got an example using scikit-learn on classification. I don't know. Let me think. Is there anything I need to say? So, I went over final exam information on Wednesday. So again. That will be basically 1 week from today, 8 a.m. on Friday, right? But you'll take it at home. So I think a couple students asked me, like, I live with roommates and stuff. That's fine, okay? You can have, it is fine if other people exist, okay? So if people exist in the background of your webcam, that's fine, okay? I will ask that when you use your webcam, don't put on a virtual background. You can have a blurred background if you're like embarrassed by how messy your room is or something like that. You know, that's fine. You can have a blurred background, but I ask no virtual backgrounds. And then just make sure your camera's working. And again, if your laptop camera or computer camera isn't working, have Zoom installed on your phone, and that's fine. I don't know if there were any other questions about the final. I think it should be okay. I mean, it's going to be similar in format to the homework, so I'm assuming everybody's been able to open Jupyter Notebooks and get their homeworks running and rendered, and you'll submit it on Gradescope as well. I have a favor to ask, and that is to fill out your course evaluation. Let me see. Let me just do a check on how many have participated. You don't get to actually find out like who participated until the very end. And again, all of the evaluations are anonymous. There's no knowing who said what, so not to worry. Okay, all right, we're at 42%, so 29 out of 68. I guess that's better than zero. But again, if you haven't filled out your course evaluation, I appreciate you taking a few minutes to do so. Higher participation always looks a little bit better. And then again, I am non-tenure track professor or non-tenure track faculty, which means I don't do research. A lot of your professors are tenure track, which means they do research. They are asking questions or trying to find answers to questions that no one has been able to answer before. It's really fascinating stuff. Basically, they are developing these machine learning techniques. Maybe not at an undergrad level, but basically, these advanced things like figuring out like what can you do with a neural network and getting it, to become ChatGPT or self-driving cars or asking even like figuring out the mathematical models that go behind a lot of these kinds of things. That's what these tenure track research professors do. Really incredible stuff. And a lot of this research is conducted at universities across the world, around the world, and also at some of the biggest tech companies. So there's like Microsoft has their research division, Google has their research division. All of these, Apple, Tesla, they all have kind of a research division that's also employs these PhDs. But as far as undergrads, your experience with, at least with teachers like myself. So I don't do research. I just teach, and so I am evaluated primarily, or actually almost solely, on my teaching ability. And so anyway, I hope you feel like I was able to teach and impart knowledge regarding Python to you, and your course evaluations get factored in during my merit reviews and whatnot. So anyway, I appreciate you taking a couple minutes to complete those. All right. So this question. Yeah.
It still works. Would it still
Yeah. The exam is kind of like, could you get it to work, all right? And if the problem says, I want you to use pandas, I want you to use pandas. The only kind of real restriction will be don't use a package that I haven't mentioned in the course. Okay, so things like you can import obviously pandas and NumPy, math, any of the stuff that I've covered and mentioned in the course. That's fine. I just don't want you there's no reason to install like TensorFlow or something to go through to get your answer. Okay, there would be no reason to do something like that. But yeah, just don't be importing or installing some kind of package from something that I haven't covered. But basically, if it's there, and then certainly functions that I haven't mentioned but that exist within the package, those are allowed. Yeah, question.
Can we turn it in the file? Do you want to just turn it into a Jupyter notebook, or do you want to
Render it to PDF and submit that. Yeah, so it'll be a lot like the homework. When it comes time to grading, we don't want to have to like rerun everybody's Jupyter notebooks. We're going to kind of go under the assumption that your Jupyter notebook runs and whatnot. So we have that, and also like when you like import data and stuff, it should be very simple. You should just use kind of a local reference to the file. But sometimes people will like import and put in like the full address. So it'll be like users / Joe Bruin / documents or / desktop / stats21 / final exams. It'll just be like this huge thing that references their exact folder on their exact computer, which doesn't transfer well when you give it to someone else. Okay. All right. I don't know. Any other questions before I just start just showing you some scikit-learn demo or something? Okay. Perhaps before we go on, let's see. Let's go to the UCLA library. And I just want to point you to additional resources. Okay. So if you're not using our school's library, you should be using our school's library. Okay, it is truly it's really great. Okay, and you're paying for it, right? You're paying tuition. Part of your tuition money goes towards the library. So get your money's worth. Okay. So anyway, you go to UCLA Library, you just go into the search, you type in whatever you want, right? But here we're going to just say like, hey, you want to do scikit-learn, okay? Sign in to place requests. Okay, yeah. All right, so yes, one of the top hits is this book, Hands-on Machine Learning with Scikit-learn and TensorFlow. Maybe the TensorFlow stuff is now a little bit outdated. It's from 2017, but it's still I would say it's still a great resource. Okay, certainly all of these scikit-learn has certainly gone through updates, but at least like kind of its core, like how you interact and how you do stuff with it, that has remained the same. I'm not familiar with some of these other textbooks. Machine learning. Oh, these are like translated from other languages or into other languages. Okay, but anyway, any of these things that say available online, you don't even have to walk to the library because I guess that's a hurdle for some people. So you can just click the available online. It will right here, online access, fully available, O'Reilly online learning. You'll click that and you will sign in. You'll search for UCLA. Sign in with my institution, and then ta-da! All right, and you can read it. Okay, you'll click continue or whatever, you'll start reading the things here. Okay, so hands-on machine learning with scikit-learn and TensorFlow. This is a great resource if you are interested in doing machine learning stuff with Python. Highly recommend this textbook. And then certainly there's a whole bunch of stuff in the O'Reilly catalog. So you can also just search for scikit-learn here. And oh, a third edition. That's really exciting. Okay, all right. We'll go with the third edition. Yeah, so they updated it, and they've added Keras, which I would say is probably preferred to using TensorFlow. So Keras is built on top of TensorFlow. So you'd have to install TensorFlow, and what Keras does is it basically gives you an easier way to interact with TensorFlow, easier way to kind of build neural networks. Now, we didn't cover any of this stuff. We haven't. I'm going to just show you like the smallest, easiest little demo with scikit-learn here. Okay, but if with all of the extra free time you guys have, that's a joke. But if you're interested, certainly, in building neural networks and stuff, the big packages for neural networks in Python are PyTorch and TensorFlow, and then Keras is built on top of TensorFlow. PyTorch and Keras are kind of the big ways. All right. Well, okay. So let's see. Maybe I can just link this, and look at that. All right. Let's add that as a resource. I'll say link to here. I gotta add a view quiz. I haven't. Okay, so I need to create a view quiz. All right. So this is recommended book. Well, I haven't looked at the third edition, but hands-on machine learning. Okay, with scikit-learn, Keras, TensorFlow. All right. So anyway, okay, third edition. Great. Let's see. The machine learning tsunami. All right. Well, anyway. Okay. Cool. Learning O'Reilly. Let's see. Just machine learning, Python, more stuff. Introduction. I haven't read these books, so I'm not familiar. Well, this has 19 5-star reviews or something. So, I mean, I don't know how. Machine learning with Python cookbook. The cookbook series are generally pretty good as well. So I have not read these, so I have no idea. But it's free, right? You're not like spending money out of your own pocket to read these books. So it's just kind of a question of like, is it worth my time reading this book? And usually I'm quite happy with O'Reilly Media as the publisher. Pact Publishing, I am less familiar with. It looks like there's even like courses, machine learning, data science, and generative AI. Yeah, okay. Little what's this? K-nearest neighbors concepts. Is this like a video? Oh, look at that.
Let's talk about a few more.
Okay, I don't want to watch this right now. All right. Well, there you go. A lot of stuff available to you, just as part of your library access. So this is like, as long as you're a UCLA student, you have access to this, and then you when you enrolled in this course, I signed you guys up for Data Camp, 6 months. Okay. All right, I'm signed out, and I don't know how to. Okay, well, but anyway, also on Data Camp, there's quite a few courses as well, and there's the projects that you can also do for practice, and not just for machine learning, but for a lot of other stuff in Python, a lot of other kind of topics that you might be interested in. So lots of resources. It's just do you have the energy and the self-discipline to get through it? So anyway, but certainly within our 10 weeks, we were only able to cover so much. My hope was that I gave you at least a base foundation in Python so that as you want to kind of go forward and do more stuff, there's more stuff you could do. It would be, I very much enjoy teaching this course, Stats 21. I think it would also be fun to have like a second level, kind of like for R, we have Stats 20 to get you started, and then we have 102A, which kind of takes our programming to a further step. And I think it would be fun to have something similar for Python, but maybe with a emphasis on, I don't know, stuff like machine learning or whatever. Okay, but anyway, let's just do a little example, and we're going to just use kind of like a toy data set, the Iris data set. I mean, I don't know if I should call this a toy data set. This is kind of your classical data set that we use for classification problems, just because the data is so clean and very nice, right? It's like this. How old is the Iris data set? It's like 100 years old now. Iris data set, the Iris flower data set. It has its own Wikipedia entry. 150. Yeah. I don't know. Okay. Well, in 1936. Okay. Well, he used it in the 1936 paper because Edgar Anderson collected the data, and he was a botanist. Okay, well, anyway, collected from the Gaspé Peninsula. Where is that? Canada. All right. So anyway, we'll load up our typical packages, and then today from scikit-learn we'll load up a couple things. The Iris dataset is kind of one of these pre-installed datasets, so you can just do from sklearn.datasets. We'll import load Iris, and that will load in the Iris dataset. So I will call in load_Iris, and when you do that, it creates a data type called a bunch. And a bunch is kind of like a dictionary, in that you have like keys, and then you have the corresponding values, but the values themselves are things like data frames, okay? So here, so within the keys, we have the data, which is used for the predictors. We have the target. We also have feature names, file name, data module, things like that. So if I go to the data and just say, hey, what are like the first 10 rows? We have this, actually it's a NumPy array. It's just this, it's the matrix of predictors. The predictor variables are sepal length, sepal width, petal length, and petal width. And so prior to working with the Iris dataset, I did not know what a sepal was, okay? But if you go, here we go. So this is kind of what an iris looks like, and these things, I always thought these were just the petals, but they're not. Apparently the petals are these parts, and these things down here are the sepals. And so you look at this, okay, and you have the things that stick up. Those are the petals, and the things that kind of fall down, those are the sepals. And Edgar Anderson, our botanist friend, went and gathered 50 specimens from 3 different species and carefully measured all of the sepals and the petals, their length and their width, and he recorded them. Okay, and so we have things like sepal length 5.1 centimeters, sepal width 3.5 centimeters, petal length 1.4 centimeters, petal width 0.2 centimeters. So that's like what, 2 millimeters, really wide. So very, very kind of small petals there. Recorded all of this, all right, and then and we measured and recorded what species of what species of iris are. All right, and so we have 50 specimens from each species. We have 3 different species of iris, and we have Setosa, versicolor, and virginica. So if you just Wikipedia iris, do you know how many? Okay, well, the answer was I was gonna be like, how many species of iris are there? 310 species. All right, I didn't know, but there's a lot. And but these 3 species, Setosa, versicolor, virginica, we have these are the Setosa. So these are like the ones with I guess they have really long sepals. Okay, and then you have versicolor. They look like this. And virginica, I guess they look like this. I mean, I don't know, but there you go. So you have these 3 different iris species, and the question is, can we, just by looking at the measurements of these different things, can we identify the thing? All right, within the iris bunch. All right, so there's also the description of the data set, and there's some information about each of these things, the 4 kind of attributes that we're using, and then what we're predicting, and then and information about the original paper from Ronald A. Fisher, kind of like the father of statistics. Unfortunately, also a eugenicist. That was why I was so interested in statistics, taking measurements on all kinds of things and stuff. But okay, so we'll go ahead and run a train test split. Okay, we'll run train test split on the iris data set. So we've seen this. So we're going to do iris.data, and that's going to form xtrain xtest. Okay, and then we'll do iris.target. Those are the things that we're going to try to predict, 0, 1s, and 2s, and that's going to be our ytrain and ytest. And we'll take 20% to be in our test set. So out of 150, we'll put 30 in our test case. Random state 1 for reproducibility. And then we'll stratify on the target variable. So that means we'll get 10 from each of the 3 species. Okay, so training will have 120 observations, 4 variables. Okay, and then we can also say, well, how many from each? So this is the bin count. This is going to kind of take and tell you how many from each species do we have here. Okay, I guess I haven't created a view quiz yet, so we'll go ahead. I'll have to do this. Question 1. What letter should we do for question 1? We'll go with C. All right, question 1 is C, and then again, I just give me a moment. I got to create the view quiz later, but I'll do that. Okay, so we'll do question 1 is C. All right, so we'll go ahead and try fitting k-nearest neighbors classifier, and so for this. I just want to do some visual exploration. We're going to take our training data, okay, and I'm going to make a data frame out of it, and then I'm going to also add the Y training to that to make our species here. Okay, so as far as our data goes, I just took the matrix and I did this. So right now we don't have any kind of variable names. I could append that and fix our data frame so our variable names take these feature names as well. But for now, let's just go ahead and we'll do Seaborn's pair plot, and then we'll color our dots using species. All right. So again, Seaborn is a handy thing for kind of visual exploration, and so here we can see for our 4 different variables, all right, which are currently unlabeled. We can see, all right, these are the 3 different species, And the question is, okay, if you saw these two variables, can you kind of classify them? And it sure seems like that, right? Like if you've got, this is what, petal length. Variable 2 is petal length and sepal width. So if you look at petal length and sepal width, you can see like anything where if you have short petal length and long sepal width or whatever. Wait, no. This is you can kind of figure out what species are. This one classifies quite easily here, but anyway, that's for exploration. So one thing we can do is we can use the k-nearest neighbors classifier. And the way the k-nearest neighbors classifier works, okay, let's see, all right, is that if you have different observations, okay, so here we have observations in, say, two classes. We have a blue class and a red class, okay. Over here in our example, we have three classes. The way k-nearest neighbors goes is you have your test case. So we select one of these, you have a new test point, and it says, maybe you say the sepal length, or variable 2 has a value of 4 and variable 3 has a value of 1.2. So you put a dot like right here, okay? And then, and what you do is you say, you draw a circle, right? And this will show you the points, the nearest points. So, right? So if I draw a circle with this radius, the three nearest points, this shows me what the three nearest neighbors are, right? If I draw a larger circle, I will get the 5 nearest neighbors. So if I choose the 3 nearest neighbors, my nearest neighbors, I have 1 blue and 2 red. And so this test case would get classified as red for 3 nearest neighbors, okay? However, if I were to pick the 5 nearest neighbors, okay, within the 5 nearest neighbors, I have 3 blue points and 2 that are red. And so, so this would get classified as blue if we had used the 5 nearest neighbors. A couple things about k-nearest neighbors is that it is very dependent upon the units that were used as far as measuring these things. So for example, let's say you wanted to do k-nearest neighbors and you wanted to kind of group people together based on height and weight or something like that, okay? So in the US, we often measure height in inches, and a person is typically somewhere between, 5 feet, 6 feet. That's like going to cover a large percentage of people. And so that's going to be, you're going to see a lot of values, say between 60 and 72 inches, okay? We could expand that a little bit more. If we go to 4.5 to 6.5 feet, that's probably going to cover everyone. So 4.5 is what? 54 inches to 6.5 being 78 inches. So 54 to 78, that's going to cover like the vast majority of people. And if you think about it, the difference between 54 and 78, that's a difference of 24 inches, okay? 24. Whereas if you talk about weight, okay, weight has a much bigger kind of range, right? If you think about weight as measured in pounds, in the U.S. we measure weight in pounds, and so on the low end, like if you put 100 pounds on the low end, and let's say 300 on the high end, okay, that's going to cover the majority of people. But now you have a range of around 200, right? And so that is, you have a much different big thing here. So so as far as like the distribution of data, you're going to have kind of a lot of like spread this way regarding weight, and then a lot smaller spread regarding height. And so if you're just drawing circles, it's probably not going to work out super great. So you might have to do things like scale your data or normalize your data so everything has a standard deviation of 1 or something like that. Okay, but anyway, as far as sklearn goes and doing the k-nearest neighbors, we're going to run the k-neighbors classifier. And again, if you go to this scikit-learn documentation, so we'll go to scikit-learn documentation, we'll go to the user guide. You know, we have a bunch of within supervised learning, we have the nearest neighbors right here, and so we can use that. I guess there's also unsupervised nearest neighbors. Okay, but generally here we're looking at the nearest neighbors classification, and so we have the k-neighbors classifier. It says scikit-learn implements 2 nearest neighbors classifiers, the k-neighbors classifiers, and then and we have the radius neighbors classifier. Okay, so the k-nearest neighbors classifier basically adjusts the radius of this circle to choose the 3 nearest neighbors, okay? Whereas the radius neighbors classifier just has a fixed radius, and so sometimes within that circle you'll have like just 1 neighbor, and sometimes you might have 5 or 10 or whatever, however many you have. And so so scikit-learn kind of implements these. Probably the k-nearest neighbors is a little bit more of a more popular choice, but anyway, you can always kind of read more about these things, and you'll click this, and you have this. So you have information regarding some of the different options you have. You have uniform weights, distance weights. The way uniform weights work is that, you know, in this diagram, basically every observation gets an equal vote. So if you have the 5 nearest neighbors, right, we have 3 blue and 2 red, and so uniform weights say, you know, you got 3 blue votes, you got 2 red votes, the blue votes win, okay? A distance-based weighting, okay, will say, you know what, nearer points, those votes count more, okay, and farther points, those votes count less. So you'd say, you know, maybe this person's vote counts for 5 votes, and this person's vote only counts for 1, or something like that, right? So maybe you have it ranked. So this gets 5 votes, 4 votes. So you have 9, and then you have 3, 2, and 1. So maybe in total, you have 9 points for red and 6 points for blue. And so if you look at the 5 nearest neighbors, if they're weighted, you know, 5, 4, 3, 2, 1, the red points would still win there. It would be 9-6 versus 3-2 or something like that. Okay, so you'd have you have these different kinds of options regarding how to do this. But we'll go ahead and just use the default of not adjusting anything, and I'm arbitrarily selecting. I want to try 5 nearest neighbors. Okay, and so if you create this, it's going to just say, hey, you got this k-nearest neighbors classifier, and much like anything else in scikit-learn, the way you fit it is you take your training data and you say, I've got my X matrix of predictors, I've got my Y array of values I need to predict, and we're going to say, go ahead and fit that, and then now we can make predictions for our test cases. Okay, so we had 30 observations in our test set, and I can just say, hey, make predictions for our 30 observations, and then let's compare that to the actual values. And it's a little bit hard, but you can see, okay, the actual value here was a 2, we predicted a 2, and you're looking for any kind of like mismatch, and it looks like we made one mistake right here. The actual value over here was 2, and we predicted a 1. This is a little bit tough to read. We have something, one of the tools that we use in classification is known as a confusion matrix, okay? So sklearn has kind of a submodule called metrics, and this is how metrics are the way we measure performance. And so you'll have things like accuracy and whatnot. And so the confusion matrix basically has horizontally, we have the truth, and vertically, we have our guess. So the way we read this, maybe I have to zoom in a little bit. Okay, the way we read this is, here it says, so remember our possible classifications are 0, 1, and 2. We have these integers for the case. And so this is row 0. So this is when the true value was 0. Okay, what did we predict? We predicted 0 10 times. We predicted 1 and we predicted 2 0 times. Okay, 100% accuracy is if you have only values along the diagonal. That's if you have only values along the diagonal, you've achieved 100% accuracy. Basically, when it was 0, we predicted 0 all 10 times. Here, for when it was class 1, when the truth was a class 1, we predicted class 1 all 10 times, and we made 0 mistakes. And the last row, we see one mistake, and this was when the truth was row 2, okay, class 2, we predicted class 0 0 times. We predicted class 1 1 time, so that's a mistake, and we predicted class 2 9 times. So this is, and we can see that that indicates this observation where the truth was a 2, but we predicted a 1, and that shows up right here in row 2, column 1. That reflects where the actual value was a 2, but our prediction was a 1, so that's a mistake. So out of our 30 observations, we got 29 of them right. So as far as our accuracy, we got decently good, but we made a couple mistakes. All right, you can also say, well, what if, here I had arbitrarily chosen, let's use the 5 nearest neighbors. Okay, what if I used the 1 nearest neighbor, okay? With the 1 nearest neighbor, I get the same performance, all right? We can also say, what if I used the 25 nearest neighbors, okay? Am I gonna get any better performance here? And with the 25 nearest neighbors, I actually get worse performance. I have 2 mistakes, okay? There were 2 times where the true value was a 2 and we predicted a 1. So when you do machine learning, okay, the way we measure our performance, here, let me give you a second view quiz answer. What do we say? We're going to say question 2 is, I don't know, A. Okay. So we'll do C and A. All right, C and A. Automated parameter search using grid search CV. So in machine learning, the way we measure performance is basically like how well can it predict on our test set and things like that. We don't have as much kind of statistical background checks like in linear regression. I don't know if you've taken Stats 101A yet. Some of you have and some of you have not. But when you do linear regression and you do Stats 101A, it takes this very kind of traditional statistics approach. And the way you measure performance, okay, you fit a model, and afterwards you do things like, let's check if any of our assumptions were violated. So when you fit linear regression, one of the assumptions is that the residuals are normally distributed. So you check to see if your residuals are normally distributed. You check to see if there's constant variance in your residuals. You check you run statistical tests. You have a t-test for each of your coefficients. You have an f-test to see if I should add another predictor variable. You have these statistical values like the AIC and the BIC, and these are all kinds of values that we use to measure the performance of our linear regression model to see if it's any good. Machine learning is very different. We say, well, we don't take as much of this statistical approach anymore. We just say, hey, if I'm able to make good predictions, it's a good model. And if I can't make good predictions, it's not a good model. And so with that in mind, we can do something. So we have like cross-validation as a tool for measuring how well our performance is. And I showed you a little bit of cross-validation on Wednesday. And what cross-validation does is it further splits your data into kind of training and testing, or assessment and validation, or analysis and assessment, or analysis and validation sets. And so one thing we might do for the k-nearest neighbors algorithm is we have this what we call a hyperparameter of how many neighbors should I use. Should I use a classifier using the 1 nearest neighbor? Should I use a classifier using the 3 nearest neighbors or the 5 nearest neighbors, the 7 nearest neighbors? We often use odd numbers for the numbers of neighbors, but I mean, you could pick an even number or something like that, right? So I might say, you know what, let's try you going anywhere from using 1, 2, 3, 4, 5, 6, 7, up to 50 nearest neighbors, okay? And then within the k nearest neighbors algorithm, we had, where did it go? We have these different options as well. So one is we have how many nearest neighbors we should use. We can also decide whether I want to use this option for, do I want uniform weights or do I want to have distance-based weights, okay? There's other things. These are more for like the convergence and stuff, but so you might say, should I try k nearest neighbors with 5 nearest neighbors with uniform weights, k nearest neighbors with 5 neighbors and distance-based weights? What about 6 neighbors and uniform weights, 6 neighbors and distance-based weights, 7 neighbors, uniform, 7 with distance? And you can say, well, oh man, that's going to be like a huge pain to have to do all of this analysis, okay? So one thing is that scikit-learn has what we call a grid search. And you specify, I want you to try out all of these different numbers of neighbors. And here I'm saying try out anywhere from 1 to 5 nearest neighbors. Also, I want you to try out uniform and distance as far as the weights go. All right? So we're going to create this parameter grid. It's a dictionary of kind of like multiple values here. And then we're going to say, all right, here, let's set up a new k nearest neighbors classifier, a k neighbors classifier. And here I don't have any kind of arguments set in here because I want the number of neighbors to be something that goes through the grid, and then as also weights, I want that to vary as well. And so I'm going to do something called grid search CV. And what this is going to do is it's going to run the k nearest neighbors algorithm using basically every single possible combination within my parameter grid. So it's going to try running this like 100 times, okay? Because I've got 50 different values for the nearest neighbors, 2 different values for the weights. It crosses them, so there's 100 different models. And it's going to do this in an automated fashion. I'm going to say do 5-fold cross-validation. And so so I run that, and it's done, okay? And so here we're going to say, all right, oh, I'm sorry, we just set this up. Okay, so now we actually run it by doing my KNN cross-validation, and we're going to fit it to our training and testing. Okay, so now it's running through all 100 models. Okay, and now it's done, right? And so it's tried this out, and we can say, all right, what were the, what set had the best, what were the parameters? And here it said 13 nearest neighbors uniform, and here, what was the score? And the best score here, I guess it got 98% accuracy when it did that. And we can say, okay, well, let's try this out. Let's try running nearest neighbors, 13 nearest neighbors, uniform weights, and see how it performed. And this is its performance accuracy. And so it made 2 mistakes out of 120 on the training data, and apparently this was the best performance, okay? And so it misclassified 2 observations when the true observation was, well, can we read this? What happened here? What are these two mistakes? The true value was a what, and what did the nearest neighbors algorithm predict? These 2. This is the true answer is in row 1, okay? True answer was classify 1, and it mistakenly predicted that would be class 2, okay? Because it's in column index 2. And that happened twice. So, our accuracy is 98%. And so here we used accuracy as the score metric. Accuracy for a score metric works well if you have balanced data. It does not work well if you have imbalanced data. Imbalanced data is basically one class is way more prevalent than the other class, okay? So, something like rare diseases, what percentage of the population carries this particular disease? It might be something like, 1/2 of 1%, okay? 1/2 of 1% carries the disease. And you can say, oh, I've created a test that has 99.5% accuracy. And you go, oh, that sounds pretty good, okay? How does this work? Oh, it just says negative every single time, okay? And if the population only 1/2 of 1% of the population carries the disease, you could just have a useless test that just says, nope, you don't have the disease, and you would achieve 99.5% accuracy, okay? It has 0% sensitivity, okay? Sensitivity is the metric of how often does it correctly classify somebody having the disease when they actually have the disease, and saying no every single time means you have no sensitivity, means you're like not able to detect it. So we have different metrics for dealing with imbalanced classes. So straight accuracy for imbalanced class, probably not the best idea. Okay, we could run it on the test matrix. With the test matrix or test data, we actually have the same kind of accuracy, 29 out of 30. And that's what we have there. Let's see. Cross-validation scores. This gives us the insight into. Here it said the overall best score was 98%. We can actually see what happened within each of the 5 different folds. Okay, there were 5 different folds, right? We had done cross-validation, 5-fold cross-validation, which means at every run we divided our data into 5 chunks. And so in our training data we had 120 observations. We divided that by 5, and so we had 24 in each test case. So we trained it on 96. Based on the 96, we tested on the remaining 24. And if we made one mistake, okay, 1 out of 24, one mistake out of 24 results in 95.8% accuracy. The other times we got all 24 correct, 24 out of 24, 24 out of 24, 24 out of 24. Here we got 23 out of 24. Overall, that's 118 out of 120. Okay. There's another classifier, the naive Bayes classifier. I've run out of time here. This is just basically you just say, hey, I want to try this other kind of method for creating a model. You just set it up, you fit it on your data, you make predictions on your test cases, and then you can say, hey, let's look at a confusion matrix, which is useful for classification. You can also do cross-validation scores. If we wanted to, there's other kinds of things we could have done. Looks like the naive Bayes classifier also gives similar performance as well. Okay, let me give you your last view quiz answer. All right, so question 3 is, we'll go A. All right, so that will be that. I've got to set up the view quiz, so just give me a minute to do that. We'll end here. It's been a pleasure being your teacher. Good luck as you study for the final exam, and we shall see you in a week on Friday. All right, and again, please consider filling out your course evaluations. Much appreciated. All right, have a great rest of your day, and good luck studying.